Happy Monday, everyone. Thanks for coming along. And today we have Bob Laramie from Computer Science at UNN giving us a talk. So Bob was awarded his PhD from Vienna University of Technology in Austria at the Institute of Computer Graphics and Algorithms. He was then a researcher at the RViz Research Centre and a software engineer at AVL in the Department of Advanced Simulation Technologies. He then moved to Swansea as an associate professor in the Department of Computer Science, and in 2020, just before COVID, moved here as an associate professor in computer science. His research interests are in the areas of big data visualization, visual analytics, and data science. If you'd like to share your screen, thank you very much for coming along and giving us a talk.
Let's see if I can get this to work. I do have slides somewhere, I just need to find them.
No worries. That's the problem I have with so many windows.
Yeah, it is. Okay, now I think I have it working.
Right, and just before we start, I'll say, as always, of course, please keep yourself muted, and we'll take questions in the chat or raise hand function afterwards.
So can everybody see the title slide?
Yeah, so we have your entire screen up.
Yeah, I guess that doesn't, nobody minds, I guess, right? They can see
absolutely fine.
My home
you can
screen.
put the PDFs onto full view, although I don't know how to do that with Apple-based products.
Hold on.
But it's fine.
How about that one?
That's it. Perfect. Yeah. Thank you.
So firstly, I'd like to just say thank you for inviting me to give a presentation. It's been more challenging than usual to talk to other groups and meet new people in the university since I did join last year. So I really enjoy invitations like this and the opportunity to meet other staff members, which has not been happening as often as I would have liked. So since nobody knows me, I will just give a very 60-second background. I was born in Boston. I studied physics at the University of Massachusetts in Amherst. Has anybody heard of UMass Amherst before? I then studied computer science at the University of New Hampshire in the US. And then there's a dashed line, that is the Atlantic Ocean. And then I jumped across the Atlantic Ocean and studied computer science at the Vienna University of Technology. From there, I went to the UK. I was at Swansea University for some years. And then last year, I moved to Nottingham in February of 2020. So that's just a little bit about my background. And this is a very short introduction to data visualization. So that is my specialty. It is data visualization, and my PhD is in the visualization of computational fluid dynamics data, and that's what I'll be talking about a little bit after. But data visualization is a very hot topic, I would say. It's in very, very high demand. And the reason is, I try to describe why on this slide. So we start with a real world challenge. For example, in engineering, you're trying to build things. Usually you're trying to build real world objects. And that takes place in the real world as a physical phenomena, like building a bridge, for example, or building a car, or building an airplane. But to build those physical objects is very, very expensive, right? To build a bridge or a car or airplane or whatever it is you're trying to build. So in order to save money, you use simulation software, right? You try to simulate the process in software as much as possible to iron out as many mistakes and problems and optimizations beforehand so that you save money when building that in the real world. So that dashed line is the transition from the physical world to the digital world, let's say. But all of those digital solutions, all that simulation software has something in common in that it outputs or produces massive amounts of data. And this is where visualization comes in. Data visualization is all about trying to create images, helpful images of very large, complicated, time-dependent data sets. That's essentially my job, is to think of innovative methods that can generate images of large, complicated data sets. And simulation probably generates the largest data sets that exist, generally speaking, right? And the question becomes, how can you visualize, for example, gigabytes of data samples in a single image? Or how can you visualize gigabytes of data very quickly, like in a few seconds, for example? That's my job, is to try to figure out how to generate pictures of data using innovation very quickly, and for very large data sets and for very often high-dimensional data sets. So a little bit more about visualization. Some of the benefits that it offers. So it offers ways to explore your data. That's for the case of when you might not have created it yourself. You might even not know what the data set is. You just want to explore it. You don't have a specific question you're trying to answer besides, like, what is this data set? What are its properties? What are the trends? What are the patterns that I can find? And what are the outliers? It's also good for analysis. So this is the case when you do know what the data set is, you know why it was generated, you know what hypotheses you're trying to address, and what questions you're trying to answer. You may have generated it yourself, for example. That's probably the case with this audience. This audience probably falls mostly into the analysis category. And of course, most people think of presentation when they think of data visualization. So how do you communicate the results of your exploration and analysis to a wider audience, right? This is one of the strengths of visualization, to use images to convey your results, right, to management or any general audience. And then there are two more that are not very obvious. One great benefit that visualization has to offer is acceleration, or saving time. So vision is our most powerful sense by far. By the way, the visual cortex occupies about a third of the brain. We can accelerate decision-making and search processes using visualization dramatically. So we can create images that let us search for patterns and behaviors or extrema or outliers and be able to identify those patterns in just a few seconds. So it offers it. Sometimes we can see things and search for things using visualization that would take months without using visualization, or might even be impossible. That's one of the more subtle benefits that's not so obvious from the outside world. Another benefit of visualization is the increase in confidence that it gives. So often in a simulation process or some other data collection process, there is a systematic error. And once you can see what you're doing, you can see the results of what you're doing, your confidence increases. You're confident that what you're doing is correct. This is also called validation by some people. So visualization is very good at increasing confidence and validation of correctness. Okay, and this is just a little bit on the technical side. We use this thing called the visualization pipeline. In this case, I'm going to focus on flow visualization, which is associated with simulation data, and especially with engineering simulation data. And we have this kind of processing pipeline that we use to visualize, for example, flow simulation data. I think in the world of engineering, you would call this the post-processing phase, I believe. Here, the simulation is just the start, right? It starts with, we call it data acquisition. And then the next stage is data enhancement, which involves some sort of filtering process. Could involve filtering, could involve resampling, it could involve deriving new data, for example, interpolation and so on. Then we have a visualization mapping phase, so taking all of the data and making it visible with visual representations. Like glyphs, for example, you're very familiar with isosurfaces, streamlines, and so on. There's a computer graphics phase, so we're always using computer graphics to generate. This is one of our standard tools, right? So we have things like visibility calculation. We add shading. If it's in 3 dimensions, we might use animation to show time-dependent behavior, for example. And then, of course, there's interaction. This is one of the major, let's say, areas of research in visualization. How can you provide interaction techniques that are helpful, that allow the user to, for example, perform queries, make selections, or perform some sort of exploration of very large, complicated simulation data sets, right? And we can map data to color, texture, opacity, positions, sizes, thicknesses, shapes, and curves. Those are our basic, that's the basic tool set that we use. These are just some images that show some examples of different flow visualizations. So this is something we call a stream surface, and it's a surface that divides the space into 2 halves, right? It's a surface that's always tangent to the vector field. These are streamlines that you're probably all familiar with. This is something called a streak surface, which is the approximation of a 2D manifold that is weightless and it moves with the flow, right? And then we have aeroglyphs, right, positioned carefully at the surface of a CFD simulation. Now, if this was a longer talk, what I would do at this point, these are all examples of some of the work we've done in simulation. I would, in the normal setting, or let's say the standard setting, my cat is here, I would take a vote. I would go through each of the options and I'd take a vote and I'd ask the audience, okay, which example would you like to see? Based on voting, audience voting. But this is an accelerated talk, right, for a short time period. So I thought I would just pick one and show it rather than having this long process of voting on their favorite. However, I suppose during the discussion phase, we can go back and revisit it if the audience is interested. So I'm just going to show the cooling jacket example, visualizing flow through a cooling jacket, not because this is the audience's favorite, but it showcases a lot of different visualization techniques in a short amount of time. So it gives you some example. And where's the slide here? This is a little bit of background about the flow through a cooling jacket. So the goal of the cooling jacket is to transfer heat away from the engine, right? So the engine doesn't overheat. And there are a few optimizations that the engineers are trying to perform. One of the optimizations is a minimization of pressure drop between the inlet valve and the outlet. And the free parameters that the engineers are allowed to to change is this gasket between the head block and the bottom block, the cylinder block. So the engineers spent hours, days, months, and years trying to optimize the position of the gasket holes. These are the holes that allow the fluid to pass from the bottom, the cylinder block, into the gasket head, into the cylinder head, and then the flow moves out, right? And there are two kinds of flow. There's a longitudinal flow component, and then there's a transversal flow component, right? And they're looking for areas where there's a lot of pressure, where there's a high pressure gradient, and they're trying to minimize those areas. So let me see if I can get that little video demo running. Where is the cooling jacket example? Oh, there it is. Good, I found it. By the way, this video is also on my YouTube channel. So I have a YouTube channel with all of the material on it. And many, many different examples like this. Can everybody see the video here?
Yes, thanks.
Let's see if it works. So yeah, this showcases several visualization techniques that, in a short amount of time. This is something we call texture-based visualization. So it shows the flow. This is the inlet, and all the patterns that the flow takes at the surface of the cooling jacket. And you can see this is a very, very complex surface. And this is good because it gives us just a brief overview of the pattern of flow at the surface in a very short time. This is what it looks like when you zoom in on one of the cylinder heads, right? This is what it looks like if you use stream surfaces seated in the cylinder in the cylinder blocks, and then watching the flow, the properties of the flow as they move into the cylinder head. That's a transparent surface, and then we can see inside to view the stream surfaces. These are color map stream surfaces. So in this example, the color is mapped to time. So the longer the flow is traversing the volume, the more the color changes. These are using particles to visualize the behavior of the flow as it passes through the volume. And this is a very challenging problem. We're not going to claim that we solve the problem of visualizing flow through the cooling jacket, but we're offering a kind of a library of different techniques that have each of which has advantages and disadvantages. So this is something we call visualizing the topology of the flow. So we're focusing here on critical points like sources, sinks, saddles, and that kind of anywhere where the velocity is close to zero, and then drawing the connections between those critical points to see how they're connected to one another. And that's something, a branch of visualization we call topological visualization. In this case, it's visualizing the topology of the flow in the cooling jackets. Those red lines are actually vortex core lines, so the axes around which flow is swirling in this case. Swirling flow is a behavior that the engineers working on this problem are actually trying to avoid. Right? If flow is getting trapped somewhere, then it can lead to overheating. And then overheating is exactly what they're trying to avoid. This is using volume visualizing to visualize specific areas in the cooling jacket that have a high pressure gradient. And that's another property that they're trying to minimize. Is in the perfect cooling jacket, there would be no pressure gradient. The pressure at the inlet and the pressure at the outlet would be exactly the same. Yeah. Okay, so that was my short 20-minute talk. I don't know how many minutes I used, probably around 20. And I guess it would be a good time for discussion and that sort of thing.
Yeah, thank you very much.
Sure.
Yeah, you were pretty spot on time, to be honest. So, as always, if anyone wants to ask a question, then please either pop it in the chat or raise your hand and unmute yourself. Given that I do flow crystallization, I find it the talk really useful. So CFD is something that I've dipped into a little bit and could be really helpful. I like particularly the visualization by time, because that's something that I think people really struggle with.
Yes, definitely. Time-dependent behavior, high-dimensional behavior, and very large data sets. These are kind of the three key challenges, really, that we're trying to solve or provide some solutions to. What kind of data is this group generating, generally speaking?
Oh, we're such a wide group. It's hard to say. So we have a lot of people who work on coatings, for instance. So creating coatings in different ways, looking at the longevity of it. It's terrible. I should definitely remember the wide variety, since I've been sharing these talks for a while now. Mm-hmm. But I've got an appalling memory. Yeah, a huge variety of things. So materials properties, obviously, being the advanced materials research group. Being one of them, so either creating, microspheres, porous microspheres, that's a big one. Pearl Sage does a lot of 3D X-ray tomography, temporal studies. Mm-hmm. Very cool. Yeah. I personally do crystallization, so it's powder and single crystal XRD is my general thing in situ, which gives you the time-based thing out of that. Do you do anything for outreach? So this is obviously something that would be completely applied, and you did state at the start of the presentation as one of it. Have you had much experience in using it for outreach or public engagement purposes?
I have. I've given talks at open days. We do some kinds of fun. I don't know if fun is the right word, but let's say more popular and accessible topics. For example, visualization of sports. Like, how can you visualize a rugby game or the events in a rugby game in a way that makes sense to trainers and coaches and can be done very quickly, like just in a few seconds, for example. So you can actually visualize a summary of a rugby game in a few seconds, right? You can imagine how difficult that is if you're an analyst, like trying to watch a game from start to finish and take notes and make comparisons between events and players and outcomes and trying to figure out strategies for different teams. So if we can use visualization to accelerate that process and facilitate that, then it's a great advantage. So yeah, we've done open days. Of course, the YouTube channel is trying to be an outreach mechanism too, right? We get a lot of traffic through our YouTube channel because all of our research videos are on there. The talks that we give are on there, and so on. So I would say that's our kind of, in some ways, main outreach. It doesn't have any special boundaries. and any special boundaries with respect to time or space. Yeah.
Yeah, that's a really good idea. We've just had a question from Sweeta in the chat who's saying, great talk, thanks. Can CFD be used to postulate reaction schematic or identify possible unknown intermediates in a reaction?
I think, well, I think CFD is used for everything, I think. It's the CFD community is about 1 million times greater than the visualization community. So I'm sure the answer is yes. I'm not an expert at CFD, but it's really simulation and CFD is being used for everything, and it's like unbelievable. I think the biggest challenge there is to try to figure out what is going on, because there's so much research going on and so many events and so much literature in this area that's probably the main challenge. Is just trying to figure out what people have done and what's new and what's not new. So yeah, I'm sure that the simulation is. I've seen it being used for so many different things. And things that you might never have guessed were previously possible.
Yeah, I've definitely seen it used for these things. Obviously, it needs to be used in combination with things like MD simulations and such like for reaction intermediates. But yeah, I have definitely seen that.
We have done some work on visualization of molecular dynamics simulations. So at the molecular level, one of the projects we worked on was to visualize the interaction with lipids and proteins. So, and that's a very challenging problem, right? Those molecular dynamics simulations, they have no bounds in terms of their complexity. And so trying to figure out innovative ways and very fast and efficient ways to visualize that kind of reaction is very challenging. But it's something we have worked on, and we have a playlist on the DataViz YouTube channel for visualization of molecular dynamics simulation. We also have a playlist for the flow visualization topic as well, and another playlist for sports visualization. Yeah. I mean, visualization is really it's a universal discipline, because everybody is generating massive amounts of data, right? And everybody has this feeling, this lagging feeling that they're not seeing everything that the data has to offer, right? That data is only as useful as it is visible. If you can't see it, I don't think it's very useful, personally.
Yeah, I definitely agree. Carl's just popped a question in the chat saying, thinking about time-dependent stuff, is it possible to interpolate easily if temporal resolution of a dataset is poor?
Yes, big topic. Interpolation is a big topic. So you have a fundamental limit on how accurately you can interpolate and recreate some behavior, right? The Nyquist limits. So your dataset samples have to be at least twice the frequency of whatever phenomena you're trying to observe. And so what you can see and how accurate it is limited by the data sampling. Right, and it's the theoretical limit is determined by the Nyquist theorem. So you can interpolate, and you can interpolate easily. It's not a big problem, but then the question is, how accurate is it, right? And visualization of uncertainty is also a big topic in the visualization community. So probabilities and uncertainty. Very, very big topics, and unsolved problems. I would easily classify these as unsolved problems. Yeah.
Cool. Thank you very much. I was going to ask if anyone online felt like just popping what it is that you work on that might be related to data visualization in the chat, please do feel free. Obviously, this recording and the YouTube channel you mentioned, Bob, we'll pop that into the AMRG team site so that people can access that as well.
Yeah, I can also put a link inside this chat to the flow.
That'd be great as well. Thank you.
This is the FlowViz playlist. I guess I would be interested to hear from people who generate large and complicated data sets that have that nagging feeling that they're not getting the full value, that they're missing, they could be missing some things. I remember asking one engineer that I worked with, are you interested in visualization? And he said, no. He said, all I care about is one number. So he was trying to summarize this gigabytes of behavior with just one number. He's like, I just care about the pressure of the flow, or at this point in this position. It's a very funny conversation, but at the same time he had this image on his screen, and he's like, oh, it has to be a perfect circle. And he couldn't decide if what he was looking at was a perfect circle or not. And I'm like, well, exactly, you need visualization for this.
Yeah, absolutely. I think it probably is unusual for an engineer to say no to visualization needs.
Yeah.
On that note, I think we'll say if anyone is interested, please do get in touch with Bob. If you can't remember his details, then come through myself or Sarah. Next week, we hopefully have Matt Lodge, but I believe he is not feeling well at the moment, so it might not happen. We will keep you up to date on that, but hopefully we will, giving us a talk on his PhD prize fellowship, which would be very nice. And I believe, I should have checked that one in advance. I believe that will actually be the last one of the year. Is that correct, Sarah?
Yes, I think that's correct.
Right, well, crikey, the year is running away. Okay, so
another
hopefully,
year.
Fingers crossed, Matt's feeling well enough, and we can send off in style. Otherwise, thank you so much, Bob, for coming along and giving us a really gorgeous talk.
Thank you for having me. Thank you. There's a full-length, like hour-long version of this talk on the YouTube channel for another group in engineering. It's like the gas to turbines group, I think they're called. Yeah. And they have a lot of simulation data in that group. Yeah. Great. Thank you for having me.
All right. Thank you everyone for coming as always, and hopefully see you next week. All right. Cheers very much.
Thanks everyone.